Do you ever think about where we are?
Sure. We're right here chatting.
No, I mean where we really are. In the universe?
Well, sometimes. I know we live on Earth. Earth is a planet that goes around the sun.
That's it?
Well, of course there's more. More planets, stars, galaxies, who knows what else.
Right. That's what I mean. There's so much I'd like to know. I wish we could explore like Columbus, but in a spaceship.
Me too. Like the moon, maybe Mars, and beyond.
Beyond what?
Well, beyond Pluto. Leave the solar system.
How would you know you've left?
I'm not sure. But it must end somewhere.
Like where?
Do a search and find out.
Okay. Where does the solar system end?
Fueled by the passions of hundreds of talented scientists, engineers, and researchers, a revolutionary new spacecraft mission is helping us map the outer edges of the solar system for the first time. The Interstellar Boundary Explorer, called IBEX, is measuring what conditions are like in the region where the solar system ends and the rest of space begins. IBEX is exploring one of the last uncharted regions of the solar system, the boundary that is formed between the solar wind and the local interstellar medium, the sea of particles that surrounds our home star and its family of planets. IBEX is mapping the boundary that defines our place in the cosmos and discovering how it may have protected the formation and development of life on Earth.
Wow, I didn't expect that answer. Tell us about our solar system and its boundary.
In order to understand the boundary of our solar system, we must start at the center, our Sun. Located 93 million miles away from Earth, the Sun is the only star in our solar system. The dimensions of the solar system are vast, stretching across billions of miles. The solar system is the Sun and its family of planets, and countless small bodies like asteroids, dwarf planets, and comets, all held by gravity in orbit around the Sun. Everything in the Sun's family slowly orbits the Sun. One way to define the boundary of the solar system would be at the edge of the Oort cloud, the cloud of small icy objects that orbit the Sun far beyond Pluto. But there is another way to define the edge of our solar system. The solar system contains what we can easily see, but it also contains important parts we cannot see. Every second, our star produces a wind of particles streaming away from its surface and pushing out beyond the planets toward deep space. This wind moves swiftly away from the Sun at speeds of 1,000,000 miles per hour. The solar wind is a plasma, an energized gas in which electrons are separated from the nuclei of atoms. making the atomic particles charged. These charged particles attract and repel one another, and as they move, they carry magnetic fields and currents that flow along with them through the solar system. The interaction of the solar wind plasma with the Earth's magnetic field causes beautiful displays of northern lights. As the solar wind continues outward in all directions from the sun, it passes all the planets, creating a huge bubble. This solar wind bubble pushes into thin clouds of other particles beyond our solar system that are flowing in the region between the stars. These clouds of flowing particles are called the interstellar medium. The outer edge of the solar wind bubble defines a boundary between our sun's sphere of influence and the rest of the galaxy. Astronomers refer to this bubble as the heliosphere.
So we live in a bubble called the heliosphere.
The sun and the planets are inside that bubble.
What is outside of the heliosphere? What about the stars?
In order to reach even the closest stars, we would have to cross the solar system boundary. The sun and approximately 200 billion other stars and gaseous regions called nebulae move along large orbits in a cosmic journey around the center of the Milky Way, our galaxy. Just like all other stars in the galaxy's flattened disk, the sun slowly orbits the center of the galaxy, like a horse on a merry-go-round, taking about 250 million years to go around once, gently bobbing up and down through the disk. As our solar system travels through different parts of the Milky Way, the heliosphere's shape and size keep changing. The heliosphere protects us like a cocoon as the sun and its planets travel through the Milky Way. Yet there's much more beyond the Milky Way. The entire universe, everything that we can detect, contains more than 100 billion galaxies, islands of stars, gas, and dust, that float majestically in groups of great clusters, separated by dark voids of mostly empty space.
Wow! I had no idea the sun moves through the galaxy like a horse on a merry-go-round. Now that's cool.
If the bubble changes its shape and size as it moves through the Milky Way, does that affect us on Earth?
Changes in the bubble can affect its ability to protect the solar system from dangerous particles coming from other parts of the galaxy. Because the solar wind plasma carries a magnetic field, it protects the solar system by repelling energetic charged particles called cosmic rays. These cosmic rays originate in other parts of our galaxy and fly at high speeds towards the inner solar system. These high-energy particles can be extremely harmful to life, but most of them are blocked from reaching us by the outflow of solar wind. Were it not for this protective bubble, life on Earth might be very different or not even exist. Although the bubble is invisible to our eyes, special instruments aboard the IBEX spacecraft are examining it in great detail. The stream of charged particles from the Sun slows down as it encounters the interstellar medium, creating several types of boundaries. This region of boundaries defines the outer reaches of the solar system.
I get it now. IBEX, the Interstellar Boundary Explorer.
Dave McComas, Principal Investigator for the IBEX mission.
My team was inspired to pursue this mission by the scientific questions we can answer. This mission gives us the chance to explore one of the last unexplored frontiers and to try to solve the mystery of what it is like at the edge of our solar system. I can hardly convey how ecstatic my whole team was when the call came from NASA that we had been selected. As IBEX operates, it is opening a new dimension of exploration and discovery beyond the planets. The focus of the new mission is understanding the solar system's boundaries, what causes them, how they change over time, and what they mean for the future of exploring our solar system. Thinking about our place in the universe and our galaxy, I see us as living in this protective bubble of solar wind. The heliosphere, this bubble, protects us from harmful radiation that would otherwise bombard us from beyond the solar system. There are unseen dangers lurking out there, and we need to understand them. In order to do that, the team had to find a way to see the invisible boundary. The images that IBEX makes helps us understand how this region protects us from the harmful radiation.
The IBEX team devised a clever way to study the whole boundary region. They placed a small spacecraft in orbit around the Earth, passing close to the Earth and then traveling most of the way out to the Moon's orbit during each pass. It is constantly collecting particles that come from the boundary region. The solar system boundary is made up of interacting particles, which don't emit visible light. Some of these particles are ejected from the boundary and travel inwards through the solar system, and a few of them are captured by the spacecraft's two unique telescopes. The IBEX scientists and engineers had to develop a way to create an image out of particles, similar to building a pointillist painting out of colored dots. They are creating a 3D map of the boundary of the solar system by charting the origins of the energetic neutral atoms captured by the spacecraft. The IBEX spacecraft has two special sensors, IBEX High and IBEX Low, which detect particles and measure the energies of the individual atoms. Over time, a map of the entire boundary region is built up from the particles that have traveled to the IBEX sensors from the edge of the solar system. The sensors aboard IBEX collect energetic neutral atoms, or ENAs. Many ENAs are formed in the boundary region of the solar system. The outward-flowing charged particles in the solar wind get slowed down and heated up as they approach the particles in the interstellar medium. When the energetic solar wind particles collide with neutral particles in the interstellar medium, they capture electrons and become neutral. These energetic neutral atoms, or ENAs, are no longer affected by magnetic fields because they have no electrical charge, so they travel unimpeded through space. Some of the ENAs travel back in towards Earth and are detected by the IBEX spacecraft.
So, IBEX can detect the invisible boundary by collecting ENAs from right here near Earth. That's so complex. Who makes sure all of this works?
How does IBEX communicate with Earth?
Looking after the sensors and the other hardware is IBEX system engineer Susan Pope.
IBEX is a complex project involving many diverse people, skills, and technologies required to design and launch the spacecraft. The IBEX team is large, consisting of hundreds of researchers and engineers at dozens of institutions from around the world. With the many different institutions working on IBEX, building and designing parts that all had to fit together, one of the major challenges we had was communicating with each other. There were many details that had to be managed, and one of the things that I spent a lot of time doing was speaking with team members by teleconference in order to make sure everyone was on the same page. If only I had a nickel for every telecon I participated in. Communication became especially important when we tested the various components of the spacecraft. We had to make sure that they could perform to the standards set by the scientists and that they could survive the rocket launch. Over the course of the building and testing of the spacecraft and the rocket, components are vibrated, placed in vacuum chambers, exposed to space-like temperatures, surrounded by loud noises to simulate the rocket launch, and test-fired. During development and testing of a spacecraft, it's normal for some things not to go as planned. Mission leaders anticipate needing to fix problems that are discovered during testing of the instrument and rocket system, and we continually worry about the things we didn't think about. It's much better for things to go wrong here, so we can fix them now rather than having problems in space where it's a little bit harder to fix. The integration and testing phase of IBEX was probably the time during the project when I lost the most sleep thinking about what could go wrong. We had a vibration failure on IBEX, and it was great to see the team come together to gather all the knowledge required to fix the problem. It was a trying but very rewarding time. I tell you, we definitely learned a lot. By working carefully with mission project managers and engineers, the team is able to make sure they have the best spacecraft and instruments possible on launch day.
IBEX was launched in the fall of 2008 from Kwajalein, a remote island far out in the South Pacific. To allow for the maximum time to collect the particles that astronomers want to image, they guided the spacecraft to a highly elliptical orbit. During each 8-day orbit, IBEX communicates with scientists back on Earth during the times when it is closest to the ground and inside the Earth's magnetic field. The data, captured by the high and low sensors, is routed to the onboard transmitter and then sent to Earth through the antennae. IBEX has 2 antennae that communicate with ground stations around the globe, depending upon its position in orbit. The stations send the signals to Mission Control in Virginia. The IBEX team also sends new commands up to the satellite during this time. By exploring the last frontier of the solar system, the IBEX mission will define the outer boundaries of the cocoon that surrounds us and protects us in the galaxy. The science team will study the bubble that shields us from lethal high-energy radiation originating from places throughout the galaxy. IBEX will paint a detailed picture of the space where the solar wind meets the interstellar medium, giving us our first complete 3-dimensional picture of our home in the galaxy.